Hello, good evening, and welcome to Regents Science Live. Tonight we're going to prepare you to not only pass, but hopefully master the physics Regents, which I know everybody out there is extremely excited for. I'm sure it's either the last thing you have to do for this school year, or it is the last thing you have to do for your high school career. So we want to end on a good note. I am Michael Eramo from Whitesboro High School. I teach physics there, and I'm going to walk through a variety of questions and topics that I have seen pop up time and time again on the physics Regents that a lot of students tend to struggle with. We also have here tonight, we have Elise. Come on over, Elise. We have Elise and we have Carson here. They are students of mine. They're going to be helping out. They will be manning the phones and our Twitter, so feel free to call in or tweet with any questions you have. If there's a certain concept you've been struggling with and you want some extra help on it, call in and I'd be happy to go over that for you. All right, you two, get back to work. Perfect. So to all of my students out there, hopefully welcome. You've seen this face before. And to all of our other students that are out there, hopefully you get a lot out of this. To my two little physics students at home, Lucas and Simon, I hope you guys are watching. And I know someday you will be prepping for the physics Regents, and I'm sure you'll both get 100s on that. To start, I thought it would be beneficial if we just go over what I think are maybe some helpful hints. Things that you should always just have kind of at the forefront of your mind when you're doing any physics question on the Regents. So I'm going to list these things out here. So we're just going to put this up here. We're going to say these are helpful hints. All right. Let me zoom in. There we go. So we've got some nice helpful hints. The first thing I would say is anytime you're reading a problem, really, physics is mainly word problems, right? They're algebra word problems over and over and over again. And so one of the things that I would highly recommend that we do is that we extract information from the problem and write it down. And we're going to model this time and time again today as we're solving some of these problems here. Next, once you've got this information, even if you are lost, even if you're saying, I really don't understand what I'm supposed to do on this problem, if you can extract that you have initial velocity, mass, and final velocity, try to find a formula that has those quantities in it. And so we're going to simply say here, find a formula. Once you've got the formula, the Regents can be a little tricky here. A lot of especially on our short answers a lot of time are worth 2 points. And to get both of those points, you need to do the following. You need a formula. So you have to write your formulas down. You have to substitute in with units. So substitute with units. And then you have to have a correct numerical answer with units. So if you want those 2 points, you have to make sure that you are paying close attention to details, the formula, and the units that are required within the problem and the units that are required for your answer. In fact, if we're talking about units, I think this is a really helpful hint, and I know that this has helped students in the past. If you forget a unit, right? Forget a unit. You don't remember. What exactly is the unit for this quantity? Well, it's easy. You can use your formula. So use the formula. So let me put an example down of what I may be suggesting here. Let's just pretend you forgot what the unit of force is, which, of course, hopefully will never happen, right? What is the unit of force, guys? Newtons. Yeah, thank you. Perfect. They got it. So it's newtons, right? But in case you draw a blank and you forget what the unit of force is, use the formula. So we know Newton's second law, sigma F equals ma. If you know the unit of mass being kilograms, and the unit of acceleration being a meter per second squared, you could claim the unit of force is equal to a kilogram meter per second squared, which is, of course, equivalent to 1 Newton. And this is an acceptable unit. It is a correct unit, and it is worthy of a point. Lastly, we're going to just go one step further with maybe what can we do if we get stuck? How can we try to find some points within a problem? A lot of times you might be given a multi-step problem where you are required to use the answer from a previous portion in the next step of the problem. So if you don't know how to do that previous portion of the problem and you leave it blank, there's no way you can continue on with the problem. So what I often tell students is that if you are stuck, make up a value. And let me give a scenario where I would say that there's some credit to be earned by making up a value. Imagine if we had an object, and we said it was a 5 kilogram object in equilibrium. So you might say, okay, maybe the first part of this question, I don't know, we'll just assume maybe this is question 61. It asks you to find the weight. And you don't remember how to find the weight of an object. So it's going to be really difficult for you to answer this. And then question 62 asks you, find the normal force. Well, the key to this problem is this concept right here, equilibrium. If we are in equilibrium, then that means the net force acting on an object is 0. And maybe we recall that fact. And so we say, okay, well, I've got a force due to gravity pointing down in this direction, and I've got a normal force which points up and perpendicular to our surface here. So I know because we're in equilibrium, the net force has to be 0. That tells me the normal force needs to equal the weight, or the force due to gravity. But I don't know how to solve for the weight. So what I would recommend doing in a scenario like this, I would pick a value. Let's just pick a number, 10 newtons. Well, we just lost credit on that problem, but now we have the ability to solve this problem. If we know that we're in equilibrium, we can answer this as 10 newtons, and we should get credit for that concept. So a nice little overview of some things that I think will be helpful for us as we begin to review some of our concepts here. Before we start looking at some problems, with my students at Whitesboro, one of the things that we go over a lot is vocabulary and word associations. I think on the Regents, a lot of times they use different vocabulary terms interchangeably on different problems, and that can throw students if they don't know how to swap those terms in and out. So, for example, a nice example is what we just looked at here. We could say that the word weight, when we see the word weight, we have to also think force due to gravity. So those mean the same thing, right? The weight of an object, the force due to gravity acting on an object, those are, in fact, the same thing. What's another one? Well, another one in line with this, sometimes we will see the term gravitational field strength, which is just a fancy way of discussing the current acceleration due to gravity at a given location. On the surface of the Earth, negative 9.81 meters per second squared. Some other terms that I think are interchangeable. Impulse. When we see the word impulse, we have to think change in momentum. When we see the word work, we also have to draw this conclusion. It's nothing but a change in energy. Another common term that I think helps is anytime we're dealing with centripetal motion questions, we can think that the word centripetal, oh, someone whispered it over here. What is it? Of course, it's center seeking. So we can say centripetal forces, centripetal accelerations, they seek the center. That's what that word centripetal means. It means center seeking. And we'll end here with just maybe one more here. We'll say the term potential difference. We sometimes refer to that as a voltage. So I think that it's helpful to see how these terms work interchangeably, in and out. And we're going to see as we go over some problems here tonight where we might call this a potential difference, we might reference it a voltage, and how the reference table sort of references these as well.
Hey, Mr. Eramo, we had a question.
Sure, go ahead, Elise. What's the question?
How do we solve for the total resistance of a parallel circuit?
Oh, that is a fantastic question. So how do we solve for the total resistance of a parallel circuit? So let's draw up a parallel circuit here. So let's see, we'll put a little note here, parallel circuits. So first thing, we're talking just total resistance, right? So I'm going to maybe expand this, and we're going to build this into a larger scale problem. Imagine if I had a parallel circuit that consisted of a 9-volt battery. Let's do a 10 ohm resistor and a 20 ohm resistor. So we've got two resistors in parallel to a 9-volt battery. So a lot of times they might ask you to draw the schematic using proper schematic symbols. So if you forgot what your schematic symbols are, on your reference table, they pretty much give you everything that you need to know here. So if I look at our electricity page, right down here at the bottom, we have our schematic symbols for our battery, for our resistors, for things like voltmeters and ammeters or variable resistors or lamps. So our circuit, we are going to include a battery, we'll include a couple of resistors, and why don't we put some meters in there as well, because I think that that's probably going to be helpful to see how they are placed. So I will put a battery. All right, I'll label a positive terminal, negative terminal, and I tend to like to label the voltages, right? So if this is a 9-volt battery, I know the voltage right here at this point is 9 volts, and the voltage down here is 0 volts. And so in parallel, I'm going to have two resistors. So here's my first resistor. All right, closed loop. We'll label that 10 ohms, and then I need my second resistor in parallel here. All right, and we'll say that that is 20 ohms. So there is our nice parallel circuit. Now let's talk about meter placement here just really quick. Voltmeter, which measures voltage, needs to be placed in parallel or across the element with which you are trying to measure the voltage. So let's just assume we're trying to get the voltage drop across this 20 ohm resistor. Then my voltmeter has to go in parallel to that or across that resistor. So there's a nice position where we can read the voltage drop across the 20 ohm resistor. And what if we wanted the current in, let's say, the current flowing through the 10 ohm resistor? Well, ammeters, which measure current, have to be placed in series. So in series, or in the same path here, I'll put my ammeter right here. I can't have it here or here because if we think about current, this is going to be the total current flowing out of the circuit. And when it gets right here, that current is going to branch. We're going to have different currents. I've got some current flowing through my first branch, I1, and some current flowing through my second branch, I2. Now, with that setup in place, the question here was, how do you calculate equivalent resistance when in parallel? The first thing that we're going to say is, when you have resistors in parallel, the overall resistance of the circuit is going to decrease. All right? When we put them in series, resistance adds up. And if you think about it, there's only one path for current to flow in a series circuit, so the current encounters every resistor. But if you look here in parallel, what we have done by placing a second resistor in parallel to the first, we have now provided a second path for more current to flow through. So our total resistance should go down. So how do we find this? Well, if we look at our reference table, we have some nice formulas for parallel circuits, and here is our equivalent resistance formula for resistors in parallel. Now, this is a tricky formula, and so I'm going to write this out. If we want, full credit on a Regents question, I'm going to have a formula. So I'm going to say 1 over my equivalent resistance is equal to 1 over R1 plus 1 over R2. So we've got some fractions here. And if we continue on with this, 1 over our equivalent resistance is 1 over 10 plus 1 over 20. And if I were to do that on a Regents, I unfortunately just lost a point because I forgot units in my formula. And that's one of the sticking points that New York State will get you on. So we're going to put some ohms symbols in here. Now, adding fractions, even the smartest of us, we kind of we botch this sometimes. We might look at this and say 1 over 10 plus 1 over 20 is 2 over 30 or something along those lines. We have to have common denominators. Of course, you could also just do it on your calculator. So I'll just do 1 over 10 plus 1 over 20, and I get an answer of 0.15. So if we look here, what I'm solving for on the left-hand side of my equation, though, is 1 over the equivalent resistance is equal to 0.15. I didn't actually yet solve for the equivalent resistance. I solved for the inverse of the equivalent resistance. And so if we think about this right-hand side of the equation as a fraction, I put a 1 under it, I have to essentially take the inverse of both sides. So I'm going to flip both sides of my fraction, and that is going to allow me to say that the equivalent resistance, and just to show it, I'll put it over 1, is equal to 1 divided by 0.15. So you have to remember this last step. So if I do 1 divided by 0.15, I get an equivalent resistance of about 6.67 ohms, which if we look, is in fact smaller than the resistances that we had started with. We said the overall resistance should decrease. What that is going to allow me to do, I can now redraw my schematic. I can draw an equivalent schematic, and instead of 2 resistors in parallel, I will put my total resistance. So I still have my 9-volt battery, and now I'm just going to put my equivalent resistor with a value of 6.67 ohms. Why might this be helpful? Well, imagine if there was a question where it asked you, what is the total current in the circuit? Well, we have Ohm's law as one of the mathematical tools that we can use when analyzing a circuit. V equals IR. But I like to say that Ohm's law needs to be applied within a specific portion of the circuit. We can apply it across this first resistor, we can apply it across this second resistor, or we can apply it across the total circuit. And if we're looking for the total current, then it would make sense to apply Ohm's law across the total circuit. So what is the total voltage in the circuit? Well, it's provided by the battery. So I'm going to put little subscript t's here for total. Our total voltage is 9 volts. We're looking for the total current. And what is the total resistance? Well, we solved for the equivalent resistance. We said it was 6.67 ohms. So if I divide now, 9 divided by 6.67, I get a total current of approximately 1.35. Oh no, I forgot what the unit of current is. Well, you can just look at your formula. Volts divided by ohms would be an acceptable answer. Or what is the unit of current? Do we remember? Amps. Very good. I put you on the spot. You did a nice job on that one. So we have our total current there. So hopefully a nice little review of a parallel circuit here, resistors in parallel. Let's just go one step further here with this question, because it is a great question. And you definitely see circuit problems pop up, I think, on the part 2s pretty regularly. If we think about the voltage drops across these resistors, I'm at 9 volts potential here with my battery, and I've encountered minimal resistive elements. We're assuming that the resistance of the wire is negligible here. So that means I have to do no work, essentially no work, to push charge through this wire. So I should be at 9 volts here, and I should be at 9 volts here. Similarly, I'm at 0 volts here, and we have encountered no resistive elements, so I'm doing 0 volts and 0 volts. So across each resistor, we are dropping the same voltage. We're dropping 9 volts across each resistor. So let's just see what happens. I'm going to apply Ohm's law across resistor 1 and resistor 2 here really quickly. Ohm's law across resistor 1, V1 is equal to I1 R1. What's the voltage drop across our first resistor? It's 9 volts. What is the resistance of our first resistor? It's 10 ohms. 9 divided by 10 gives me a current of our first resistor of 0.9 amps. Let's do the same analysis here on R2. We're going to take Ohm's law and apply it across our second resistor. What's the voltage drop across the second resistor? It's 9 volts. What is the resistance of the second resistor? It is approximately 20, well, it's not approximately, it is 20 ohms, right? And so if we do 9 divided by 20, we get a current through our second resistor of 0.45 amps. And here's where it all comes together, because if you look here, we have what we'll call a node here at this point. The current coming into a node must equal the current going out of a node. Current has to be continuous. And so if you look, we had 1.35 amps coming in, and how much do we have coming out? Well, we have 0.9 amps here, 0.45 amps, and if you notice here, our total current is going to equal the sum of the current in our branches. And that works out quite nicely, and that is something that is given for us on a parallel circuit right here on our reference tables. So great question for whoever called in. Hopefully you feel a little more confident here on parallel circuits. I'll check my helpers. Anything right now? All right, that means we get to choose, right? We get to choose what we are going to look at. I think I will let's do a modern physics question. I think that's a great idea. There's always a couple of questions in the short answers on modern physics, whether it's that energy level diagram in the production of the photons of light, or as we see right here for the hydrogen atom and the mercury atom, or whether it's on our classification of matter in the standard model with quarks. And physics teachers all around will tell you that modern physics, it always gets saved to the last unit that we do, and there's a lot going on, and so sometimes what ends up happening is the teachers and the students, we tend to rush through this. So I think it would be very helpful for us to see a nice example question. So I am going to open up a practice problems that I have here, and let's look at one. All right, so this is taken from one of our Regents here. Let me zoom in a little bit. So it says tritium is a radioactive form of the element hydrogen. A tritium nucleus is composed of 1 proton and 2 neutrons. When a tritium nucleus decays, it emits a beta particle. And if you don't know, a beta particle is nothing but an electron here in this case. And it also produces something known as an antineutrino. So we're creating antimatter now as well. And it does this to create a stable form of helium. During beta decay, a neutron is spontaneously transformed into a proton, an electron, and an antineutrino. All right, so that is a lot to take in. But if you see like what we did here, we underlined some key information, some things that I think are maybe going to help us. If I'm reading this problem and I maybe don't know what I'm doing, I at least can say, hey, I've got, I've got neutrinos, and this sounds like it's like a modern physics. We're talking about decay. I'm going to open up my reference table to this page right here and have the standard model right out here for me. So our first question here, 52, asks, what is the total number of quarks in a tritium nucleus? Well, if we look here in the reading, it says that the nucleus is composed of 1 proton and 2 neutrons. So 1 proton and 2 neutrons. Now, if we head to our classification of matter, we can see that matter can be subdivided into 2 primary categories. A lepton, which is fundamental. And our leptons, great examples. We have our star particle, the electron. We have the muon, the tau. And then if you notice, we have some of our neutrino particles. So we'll come back to those in a moment. Otherwise, we have hadrons. And a hadron is something that is not fundamental, that can be broken down into smaller particles of matter, and those particles are known as quarks. And depending on the composition of the hadron, whether it is made up of 3 quarks, a baryon, or a quark and an antiquark, a meson, we can kind of get an idea what's going into that. So protons and neutrons are baryons. So they are made up of 3 quarks each. And if we look here, what is the total number of quarks in the nucleus? Well, we have 1 proton. So that's going to give us 3 quarks. And I'll just use Q for quark here. And we have 2 neutrons. Well, a neutron is a baryon. So a neutron has 3 quarks in it. But we have 2 of them here. So this is going to give me 6 quarks. And so if I add those up together, my total quarks, I'm going to have 9 quarks in total here. If we look at question 53, it asks, what is the total charge in elementary charges of a proton, an electron, and an antineutrino? All right, well, a proton, you might sit there and say, I know the charge of a proton. It is positive 1.6 times 10 to the negative 19th coulombs. And you would be correct. However, this is asking for that charge in elementary charges. And so if we look on the front of our reference table, here is that charge, 1.6 times 10 to the negative 19th coulombs. That is essentially what we call 1 elementary charge, the charge of a proton or the charge of an electron. And so here we're going to say that the proton contributes positive 1 elementary charges, while the electron contributes minus 1 elementary charges. And so now the question is, well, what about the antineutrino? Well, if we go back to our standard model, under our leptons, we see that all of our neutrino particles have a charge of 0. But this isn't a neutrino. This is an antineutrino. So we have to understand the relationship between matter and antimatter. And it boils down to this. Antimatter has the same mass, but the opposite sign charge as its matter constituent. So, and that tells you it right here. For each particle, there's a corresponding antiparticle with a charge opposite that of its associated particle. Well, neutrinos are 0, so what's the opposite of 0 here? It's still 0. And so the antineutrino has a charge of 0, and if we add these up, positive 1 plus negative 1 plus 0 gives me an overall charge of 0 elementary charges. Another quick way that we could look at this problem, if you look in the reading, it tells us that during beta decay, it is a neutron that is going to transform into the proton, the electron, and the antineutrino. And we know the overall charge of a neutron is 0 elementary charges. And charge has to be conserved. So the total charge here of the proton, the electron, and the antineutrino will also be 0. Last question. I feel like this is an either maybe you know it or you don't. It says, what fundamental interaction is responsible for binding together the protons and neutrons in a helium nucleus? So the force that is responsible for holding the nuclei of atoms together, the force that overcomes the electrostatic force of repulsion of the protons and binds neutron-neutron, proton-neutron, and proton-proton pairs together, is the strong nuclear force. So there is a really nice wrap-up of a nice modern physics problem that you might see. You might see maybe in a part C here. Did we have a question?
We did. How do you find the gravitational force of a block on an inclined plane?
Oh, that is a fantastic question. The incline plane. I don't know about students in other areas, other schools, but my students, and you guys, maybe you can agree to this, the incline plane problems were challenging. They are awful. We have it on record that they were awful. They are awful. They are very awful because so much, and here's why I think they are awful. You know, from middle school, maybe even elementary school, we have been conditioned to think about a plane, a Cartesian plane, as an x-axis, and a y-axis. And there's nothing wrong with that, right? We've got two perpendicular vectors, two axes, we'll say, that are perpendicular to one another, a horizontal axis and a vertical axis. But on an inclined plane, it becomes a little trickier. And so what I end up doing is I take this Cartesian plane, x and y, and I simply rotate it. And let me explain why. I'm going to draw a plane here. Let me say, yep, I'll draw a plane. Well, let me draw my incline first, and then we'll show this. So here is my incline. Let's pick an angle. How's 15 degrees? How's that sound? I think that's a great number. So here's our angle of 15 degrees. We're going to put our block on here. And let's assume that the block is at rest. All right, so the block is at rest. At rest. And let's give the block a mass of, we'll say, I don't know, 22 kilograms. Perfect. And so if it is at rest, we know that this block is in equilibrium. That means the forces must be balanced acting on it. So let's dive through and look at what some of those forces are. Well, the first thing that we know is there is always a force due to gravity acting on an object. And that force due to gravity always acts straight down. Whether or not we are on a flat surface or whether or not we are on an inclined surface, the force due to gravity always acts straight down. So I'll draw that vector. So there's Fg. And so let's just talk about the force due to gravity. How do we solve for that force? Well, we can say Fg, the force due to gravity acting on an object, or the weight of an object, is simply its mass, m, times the acceleration due to gravity at the location. So we're going to assume we're doing this on the surface of the Earth. So the acceleration due to gravity is negative 9.81 meters per second squared. So if I do 22 kilograms times negative 9.81 meters per second squared, and I multiply these two values together, 22 times 9.81. And you can see I'm using the positive value here. The Regents is really forgiving when it comes to solving for a vector quantity versus giving its magnitude. And here we really do have the direction of that weight, that force due to gravity, pointing down. So I'm going to claim that the force due to gravity is about 216 newtons. Sure. And so I'm going to write that in. 216 newtons. Now, let's come back to my previous axes, my flat surface, right? If I have my block on the flat surface, I know the force due to gravity points down, and that was 216 newtons. And if the block is in equilibrium, then if there's a downward force of 216 newtons, there must be an upward force of 216 newtons to cancel it out. And what do we call that upward force? Well, in this case, we call that the normal force. It is the force provided by the surface to lift it up. And so we can just say, hey, these things must be equal and opposite. And the problem is done, and it's really nice. However, here, it's not as nice because we're not on a flat surface. And when we think about the normal force, what direction does the normal force point in? A lot of times students will say, oh, the normal force points up. But that is only true on a flat surface. The better answer is that a normal force always points perpendicular to the surface. And so perpendicular to our surface, if we look here, is going to be a 90-degree angle. So that is up in this direction. So we'll label that Fn. And if you look at our diagram, these two vectors are not pointing in opposite directions. So they're not going to cancel each other out perfectly. However, what we can do is we can look at our force due to gravity, and we can break this down into two different perpendicular components. We can break the force of gravity down into a component that is perpendicular to our plane in the direction of the normal force. And I'll call this Fg perpendicular. It is our perpendicular component. And I can break it up tip to tail. So here's one component. At the tip of this component, I'll draw the tail of my next component. I can draw a component that points, essentially, if you look, this component, if I just slide it up here, it points parallel to the plane. It points down the plane. And so I can call that Fg parallel. And so I end up getting two perpendicular vectors, but they're not x and y. Instead, they are in a coordinate system which we'll call perpendicular to our plane and parallel to our plane. And so if we look here at our original xy diagram, right, these two coordinate systems, imagine if I just took this system and I rotated it. Now I've got a coordinate that is perpendicular to my plane and a coordinate that is parallel to my plane. It's the exact same type of problem, the same type of math that you did probably within the first couple of weeks of physics we can use here. Now, one thing, and I often tell my students, you just got to know this. We could go through some of the geometry that it gets you there, but if the angle of your ramp is 15 degrees, then this angle of this triangle is also 15 degrees. All right, and that's something that I just say, you have to know it, just remember that. You can make that connection. And so now that we look, we have an angle, and essentially this serves as the hypotenuse of our right triangle. If I turn my paper, here's our right triangle. We've got perpendicular components, and there's our hypotenuse. So we can solve for these values, right? We can solve for these values. So if we look, let's solve for Fg perpendicular, this perpendicular component of the force of gravity. It is the side adjacent to my angle, and I have my hypotenuse. So what trig function is adjacent and hypotenuse? Well, it's going to be cosine, right? It's cosine. Perfect. So I'm going to say the cosine of my angle is adjacent over hypotenuse. So I take the cosine of 15 degrees is equal to my adjacent side, which is what I'm calling the perpendicular component of the force of gravity, divided by my hypotenuse. My hypotenuse is the overall force of gravity, which was 216 newtons. A few things about this. In a problem like this, if we're mentioning units, the degree symbol is required. And you always want to make sure that you are in degree mode, all right? Despite what your math teachers tell you, we do not want to be in radian mode, all right? They're evil. We're a lot better. So keep your calculators in degree mode. If you're not sure at the Regents, you say, I'm not sure, raise your hand, have someone come over and check it for you. It'd be a shame if you were in the wrong mode and you lost points because of that. So I'm going to take the cosine of 15 degrees, and I'm going to multiply it by 216, and I get a value of about 208.6 newtons. So my perpendicular component of gravity is 208.6 newtons. I'm going to label that in. On my inclined plane now, I now have that this is 208.6 newtons. Look here. If this vector is 208.6 newtons, there must be a vector in its opposite direction canceling it out if this thing is in equilibrium. What vector is that? It's the normal force. So we can claim our normal force must be equal to 208.6 newtons. All right, let's do our other vector. Let's do this parallel component of gravity. Well, now what I have is the side opposite my angle, and I still have my hypotenuse. So opposite and hypotenuse would give me sine. So I'll say the sine of my angle is equal to the opposite side divided by our hypotenuse. The sine of 15 degrees is equal to my opposite side of my triangle, which is the parallel component of gravity, divided by my hypotenuse, which is 216 newtons. So again, I'll take the sine of 15 this time and multiply it by 216 newtons, and I get 55.9 newtons. So we'll say Fg parallel, this parallel component of gravity, is equal to 55.9 newtons. 55.9 newtons. Well, wait a minute. If this is 55.9 newtons trying to pull it down the ramp and our block is in equilibrium, there must be some force that points up the ramp that also has a magnitude of 55.9 newtons to essentially cancel out this component of gravity that is trying to pull the block down the ramp. And what force would that be? Well, it's going to be the frictional force. Look at that enthusiasm. I love that. That is fantastic. It's the frictional force, right? So we can say, hey, the force of friction here is going to equal 55.9 newtons. So a couple of takeaways on this inclined plane problem, which is a wonderful question. In my experience, and I may be wrong on this, I don't think you tend to probably won't get a short answer question in regards to this. Maybe you will, but a lot of times I see this more as a multiple choice question, all right? A multiple choice question where maybe you are very quickly asked to get the force of friction, or you're quickly asked to get the normal force. And if we look here to summarize this problem, because we did do a lot, we can essentially say on the inclined plane, the normal force is going to equal the perpendicular component of gravity, and our force of friction, if we are in equilibrium, of course, is going to equal a parallel component of gravity. And so that's like a really nice summary and a really nice recap here. So whoever called in, hopefully you feel a little bit more confident about the daunting inclined plane problem. I really hope you get a question on it so you can knock it out of the park. Great question. Thank you for calling in. Any others right now, folks? All right, so we get to pick, right? That's like the beauty of this. We get to do whatever we want. Is there anything you guys want to see? No, well, of course, my students, they're confident. You guys are confident, right? Yeah. Of course you're confident. Well, I've got a list of things that we could look at. Let's look at maybe a work energy question. I think that this is probably a great type of question to look at. So let's do this question right here. So I think the Regents really likes to test the concept of the work, what we'll call the work energy theorem, and which boils down to saying that the work done on an object is equal to the change in that object's energy. So for example, if I got my calculator right here, if I want to change the calculator's energy right now relative to the table, it has 0 joules of energy. If I want to give that calculator energy, I have to do work. I have to apply some force through some displacement, and the amount of work that I do is equal to the change in energy of this calculator. And so this question here really kind of hits on these ideas. So it says, a student pushes a box weighing 50 newtons, 6 meters up an incline at constant speed. Okay, we got to stop right here. Constant speed is one of these like alarm phrases that I say over and over and over again. What does this mean? When you see constant speed, anytime I read this problem, I always come to 2 conclusions. If we're moving at constant speed, that tells us that the acceleration of our object is equal to 0. And if the acceleration of our object is equal to 0, that means the net force acting on the object should be 0. Doesn't mean there are no forces acting on the object. It just means that the net force, if you take the vector sums, they'll equal 0. So like, you might have equal and opposite forces. All right, so we've got that out of the way. It now says this student applies a force of 25 newtons parallel to the incline. The top of the incline is 2 meters higher than the bottom. All right, so we've got, hey, look at this. We've got an inclined plane here, but in a different context. So 54, 55. So this would be a 2-point question on the Regents, one where you have to make sure that you have a formula, you substitute in with units, and you have an answer with units. Asks us to calculate the total work done on the box by the student while pushing the box from the bottom to the top of the incline. All right, so we want to get work done. So let's look here. There's a couple of ways that we can approach this problem. The first thing that I'm going to say is if I look here, does it mention anything about this ramp being frictionless? it doesn't. So I think we have to assume that there might be some friction between the block in this ramp, right? Maybe it's wood on wood, or maybe this is a waxed ski on snow, okay? These are the values. In fact, let's just go here while we're here for a nice friction problem. On the front of our reference table, we have our approximate coefficients of friction for various surfaces. So this types of surface are important. And we have the kinetic versus the static case. The kinetic case being when the object is in motion, and the static case being when the object is not in motion or when the object is just about to go into motion, right? So if you're applying a force to move an object, the object is not yet moving, it's just about to, so that would be the static case. Those are there. It's important to point these out. So we're going to say that, hey, friction might be present, and so we're going to come back to that. So let's think about how we calculate the work done. So we'll say 54. So work, if we look at our reference table on the back here, work is force times displacement, or a change in total energy, which is exactly what we said. Except I have one problem with that equation, right? If we use work is force times displacement, I would say 8 times out of 10, 9 times out of 10, that is going to be good enough. But do we want to be good enough? No. Of course not. We want to be Great. I didn't know where we were going with that. We want to be great. We want to be great enough. And so oftentimes, maybe, every couple of times, every 2 out of 10 times, they're going to throw you a curveball on this. And if you use work as force times displacement, you're going to be wrong. Because really, the key idea here is it is the force that is in the direction of the displacement. It is the force that causes the displacement. And so how do we take that direction into account? Well, hopefully you know, is we tack on a cosine of theta, where theta is the angle between these two vectors, our force vector and our displacement vector. So I'm going to use this representation, even though I think on this problem it's not going to really matter too much for us. So if we look here, the work done by the student is the force. And this is where it gets tricky, because if you look, we have a 50 Newton block, and we know, okay, 50 newtons, that is the weight, or the force due to gravity. And then we have an applied force, so I'm going to write that as FA, an applied force of 25 newtons. Well, in this example, which force is the one that is doing the work? It's the 25 newtons. The 25 newtons is the force that's pulling the block up the ramp. So I'll plug in 25 newtons. What is the displacement of the block? Well, we have a couple of different displacements. We have 6 meters going up the ramp, and we have 2 meters of vertical height. Well, in this case, the block is undergoing a displacement of 6 meters. It's moving up the ramp. And now if we take into account this cosine theta, we can ask ourselves, what is the angle between those two vectors? Well, my force is up the ramp. My displacement is up the ramp. And so if we think about it, what is the angle between up the ramp and up the ramp? They're parallel to one another. So the angle here is going to be 0. And cosine of 0 is one of the nicest numbers out there. Cosine of 0 is 1, all right? So this boils down to give us 25 times 6, which is 150. And 150, work. What is the unit of work? Well, if we look here, work is nothing but a change in energy, so it has to be the unit of energy. So we have 150 joules. Now, we're going to go one step further, I think, with this problem. And let's talk about what is the change in potential energy, right? So we just did the work side of this argument. What is the change in energy? So when the block comes all the way up here, I just did 150 joules to pull that block up the ramp. I would expect, by the work energy theorem, that the block has gained 150 joules of potential energy. Well, let's figure it out. Our potential energy formula is the mass of the object times the acceleration due to gravity times the height of the object. If you look here, we are given 50 newtons. 50 newtons is not the mass of the object, but rather it is the product, mg. That's the weight of the object. So I'm going to substitute in 50 for this product, mg. And what is the height of the block? Well, at the end, the vertical height is 2 meters. And if we look, 50 times 2, well, wait a minute. The potential energy gained by the block is 100 joules. So these are not equal. We did 150 joules of work to bring the block up the ramp, but at the end, the block has only gained 100 joules of potential energy. So where does the extra 50 joules go? Well, we had mentioned that nowhere does it say that this ramp is frictionless. So if we think about the energy right here at the end, sure, there's gravitational potential energy. But there is also this thing known as internal energy, Q. Internal energy would be heat developed through friction, sound, those types of things. And so we can look here and we say, hey, if we did 150 joules, we only ended with 100 joules of potential energy, then our internal energy, the energy lost due to friction, is going to be 50 joules. And so I've seen that come up quite often, these internal energy types of questions. In fact, if you look at question 56, it says, describe what would happen to the total work done. So describe what happened to the total work done on the box by the student to push the box 6 meters up the incline at constant speed if the coefficient of kinetic friction between the box and the incline were increased. So if we added more friction, right, that means we're going to increase this. It's going to be harder for us to move that block up the ramp. We're going to have to work harder to overcome friction. Maybe instead of having the, waxed ski on snow with a coefficient of friction of 0.05, maybe it's wood on wood at 0.3. So the amount of work that we would have to do in 56, it would also have to increase. I think we might have a call coming in. So Carson, what do we have?
We have a tweet that came in.
A tweet? All right, let's hear it.
Asking to go over some conservation of momentum problems.
Oh, that's a great question. In fact, I recall we did some conservation of momentum problems, and what did lots of students lose points for? Do you remember?
Not taking into account the direction.
That was exactly it. Not taking into account the direction. So imagine if I have two objects that are moving towards one another, all right? They're moving towards one another. If one of them is moving in the positive direction and one of them is moving in the negative direction, we have to take velocities, not speeds here when we talk about momentum. So the direction, positive or negative, is going to have a big effect. So let's look at an example here. We'll pick some numbers. We'll pick some cars here. Let's see. We'll do a couple here really quickly. So imagine I've got, sure, I have an object here, all right? So object A, object B, I'm just going to pick some numbers. I'll say the mass of this is 1.5 kilograms. The mass of this is 2.2 kilograms. I will say that car A has an initial speed, V1, we'll call this mass 1 and mass 2. V1 will be 2.3 meters per second, and V2 will be, 5.1 meters per second. And so let's assume that when we talk about conservation of momentum problems, we typically have two scenarios. We start with two objects, and they come in, and they bounce off of one another. And we call that the elastic collision. It's elastic, so it's bouncing off. We also then have the scenario where two objects are moving, and then they collide and they stick together and then move as one object. And that would be known as the inelastic collision. And so in this example, we're going to assume that these two objects, they stick together, all right? So there's some, maybe it's like a car wreck, and these two cars, they stick together, and now the question is, which way is it moving? Is it moving this way? Is it moving this way? What is the velocity of this wreckage after this collision occurs? Well, the conservation of momentum tells us that if we take all of the momentum terms and add them up prior to some event happening, so sigma pi, that sum will equal the sum of all momentum terms after the event happened, so sigma pf. And in this case, what is our event? Our event is this collision that's happening between cars. So here we have our initial, and here is our final. Sometimes you might see it as maybe a gun being fired, or a clown getting shot out of a cannon, or two blocks that are being held together by a spring, and the spring releases. All of those things, the spring releases, the cannon firing, those are the events, all right? So look before the event, look after the event, and try to look at the terms, the momentum terms. So prior to our event here, our crash, I have two objects. So I'm going to expand this sigma pi as the first object's initial momentum, m1 v1 initial, plus m2 v2 initial. There's our second object's momentum. Now, here's where it can get tricky for students. After our event, after our collision, how many objects do I have? Well, we said that this is going to be an inelastic collision, where our two objects, they travel in, and then they stick together and they move as one. So we have one single object. So the question is, what would be the mass of this object? Well, if these two objects stick together, we are going to say that the mass is the combined mass m1 plus m2 times its final velocity, whatever direction it's moving in. So let's see if we can plug in some numbers and determine, given these starting conditions for this collision, how is this wreckage going to move at the end? So I'll plug in mass 1, 1.5 kilograms. I'll plug in V1. It's moving to the right, so I'm going to make that 2.3 meters per second, plus mass 2, 2.2 kilograms, times V2. Now, here's where, when we were reviewing, a lot of my students lost credit on a point like this. If we say to the right is positive, then this velocity being a vector, magnitude and direction, we have to negate that velocity. So this becomes negative 5.1 meters per second. That's going to equal, so those are our initial terms. Our final term, mass 1, 1.5 kgs, plus 2.2 kgs, times our final velocity. So if we sit here and we calculate this really quick, I get 1.5 times 2.3 gives me 3.45. Earlier, I had mentioned that for full credit, you need a formula. You have to substitute in with units, and then you need an answer with units. What I tend to do, here's my formula. I've substituted in with units, and then I tend to drop units as I do my calculation, and then I bring them back right at the end. So 3.45, and then I have 2.2 times negative 5.1 gives me minus 11.22 is equal to 1.5 plus 2.7 gives me 3.7 V final. So continuing on with our calculation, 3.45 minus 11.22, I get negative 7.77 is equal to 3.7 V final. I'll divide both sides by our combined mass of the car of 3.7, and I get a final velocity of negative 2.1, and here is where I will bring my units back in of meters per second. What that tells us, our initial question in this type of problem was, how is this wreckage going to move after the collision? Well, it's going to be moving to the left. And I guess we got to ask ourselves, does that make sense? Well, look at our initial momentum. The lighter car, the less massive car, was moving with a slower velocity to the right. So we had a lot more momentum here in the negative direction, and that's why we're winning out here. So great question to whoever asked that one. Hopefully that helps you with our conservation of momentum. Elise, we got another one?
We got two relating to the projectile motion. How to calculate the distance of a projectile.
Perfect.
And how to calculate the amount of time a projectile stays in the air.
Oh, those are great questions. And we have to figure out, because when we talk about projectile problems, there's a couple of different ways I think we can approach it. We can approach a projectile as something that is, launched at an angle, and so it's going up and horizontally and then comes back down and lands back at its starting height. Or we can look at an object that is maybe rolling off of a surface. And so really, I think we're going to hit on both of these to sort of differentiate between these two situations. So let's do what I think is maybe the easier one first. So this is what we'll call the rolling problem. Rolling. There's a great lab that I know a lot of physics teachers do in the area on this rolling projectile problem. They give students a marble, and then they give students a target, and they say, you got to figure out, you're going to launch this marble across the table, and you got to figure out exactly where it lands, and the bullseye has like grade numbers in it. So a bullseye is 100, and then it's 90, and then it's 80, and then it's 70, 60, and if you miss the paper, I think that's, what do we say? That's just, it's too sad to even think about. We can't discuss what grade that is, but it's a great lab. I think we call it the Shoot for Your Grade lab. So let's try to envision a problem for the Shoot for Your Grade lab. So let's just assume I've got some table. So here is my table. And I don't know how tall this table is. Let's assume it is 0.8 meters high, all right? So our table is 0.8 meters high, and I've got some ball that is going to roll off of this surface with an initial velocity. Now, watch how I draw this diagram here. On this horizontal surface, the velocity vector is going to be completely horizontal. the ball's moving across the surface, right? Gravity has not begun to accelerate it downwards until it leaves the surface. So we're going to claim our initial velocity here to be, I don't know, we'll pick a number. We're going to say this thing's moving pretty quick. We'll do 3.2 meters per second. And so we know the ball's going to leave the table, and it's going to follow a trajectory known as a parabola. And it's going to land some distance away. All right, and so we call that maybe the horizontal range. Let's just quickly, I'm going to chart the ball here at different locations on this parabola. And let's look at the velocity vectors of these this ball. So I'll do, I think I got a blue pen, perfect. So our initial velocity vector was 3.2 meters per second. Let's just look at the x vectors here. The x component of this velocity is going to remain constant the entire trajectory. So v initial, the overall velocity of the ball to start was 3.2 meters per second, but all of that velocity was in the x direction. None of it is in the vertical direction. So when we're here in our trajectory, Vx is still 3.2 meters per second. When we're here, Vx is still 3.2 meters per second. And when we're here, Vx is still 3.2 meters per second. And there's a reason why, a key takeaway. For a projectile, the horizontal acceleration of any projectile is what? It's 0. Perfect, Elise, that was great. It is 0, right? There's no forces acting on the projectile in the horizontal direction, so the acceleration has to be 0. However, it's a different story in the vertical direction. So if we look in the vertical direction, what is happening? Well, right here, if all of this velocity is in the horizontal direction, none of it is in the vertical direction. So we have no vertical velocity until the ball leaves the table and gravity begins to accelerate it. And what does it mean to be accelerated? Well, it means that your velocity is changing. And so initially, we might have a very small vertical velocity vector, Vy. And at our next snapshot, it's going to be bigger, Vy. And at our next snapshot, it's going to be even greater. And the reason why is because our vertical velocities, they are changing due to the fact that we have a vertical acceleration for any projectile, which is our acceleration due to gravity, negative 9.81 meters per second squared, anywhere in its trajectory. So with these things laid out, let's see if we can do a couple of things that might be asked of you. Can we determine how long the projectile will be in the air? And can we determine how far it might travel? So let's start with time. So let's do time. Zoom out here, perfect. So let's do time. I always like to say, when solving a projectile problem, you have to pick a direction. You got to keep things separate, right? We don't want to mix horizontal quantities and vertical quantities together. We have to separate them. And so it might be helpful for you to write a little chart, x and y. We're going to keep things separate. So let's talk about the horizontal displacement. In the horizontal direction, we have no idea how far the ball goes, so I'll call that x, question mark. Vx initial. We know what our initial horizontal velocity is. In fact, it never changes. We said it's 3.2 meters per second. Because it never changes, we know what the final horizontal velocity is. Vx final is 3.2 meters per second. We had said that the horizontal acceleration for any projectile is 0. Let's now look in the vertical direction. What is the vertical displacement of the ball? Well, here we go. Horizontal displacement we don't know, but in the vertical direction it starts up here and it ends at the ground. So what is its vertical displacement? Well, it has to go down 0.8 meters. I tend to like to use the displacement here, so I like to put a negative 0.8 meters. I don't think you'll lose points if you put positive here. I think the math works out, but I like to put a negative here. Otherwise, I think maybe what would happen is you have to take a square root of a negative number, and typically when that happens, students, correct me if I'm wrong, if you're doing a problem and it tells you to take a square root of the negative number, don't you just chop the negative sign off and you're like, I'll just take the square root of the positive number, and math works, right? So I think that's kind of how it would play out here. If we look at Vy initial, all right, so what is Vy initial? Well, if you notice here, right here, we had no velocity vector in the vertical direction. And that's because Vy initial is 0. All of our velocity points in the horizontal direction initially. Vy final, I don't know what it is. And maybe in the context of this problem, I don't necessarily care. That's OK. our vertical acceleration for any projectile is negative 9.81 meters per second squared. And so if you look, we've just charted out many of our kinematic quantities, but there's one that's missing, and that one that's missing is time. And the reason why it's not down here yet is because we've separated it into the horizontal and vertical quantities with vector quantities, displacements, velocities, and accelerations. But time is a scalar. It doesn't care about direction. And so I'm going to write time right down here at the bottom that sort of splits the difference between these two columns. The time the projectile has to fall to the ground is the same time the projectile has to move itself forward. And so we're going to see how, looking in one direction, we can solve for that time, and then apply it to the other direction. To solve for time, we'll always begin by looking in the vertical direction. So I like to start with one of our one-dimensional kinematics equations, d equals VIT plus 1/2 AT squared. And now I'm going to take this one-dimensional kinematics equation, and I'm going to be very specific. I'm going to apply it to a two-dimensional problem, and I'm going to pick a direction. I'm going to pick the vertical direction. So we're not talking about any old displacement, but a vertical displacement, y. We're not talking about any initial velocity, but the vertical initial velocity. Time's a scalar. It does not care about direction, so we'll leave that as t. I don't want any old acceleration. I want a vertical acceleration. And again, time's a scalar, so we'll leave it as t. And now that I have just vertical quantities, I'm going to highlight that. I'm going to say, ooh, right here, just vertical quantities. No horizontal values. All right, we're keeping them separate. Let's substitute in. So my vertical displacement of my ball is negative 0.8 meters. My Vy initial, my initial vertical velocity is 0. So this whole term drops away. And we get 1/2 my vertical acceleration, which is negative 9.81 meters per second squared, times our time interval squared. And this is the time the ball has to fall that 0.8 meters. So if we look here, I'm going to do 1/2 of negative 9.81. 9.81 divided by 2 is 4.9, we'll say. And so if I do 0.8, negative 0.8 divided by negative 4.905, I get positive 1.631, we'll say, equaling t squared. And this is where it's nice to negate your displacement, because now when I take the square root of both sides, I'm taking the square root of a positive number, and I get a time here of 0.4, we'll say 40 seconds. So that means our ball has 0.4 seconds to move down the 0.8 meters. But during that 0.4 seconds, the ball's velocity is just constantly, continually moving it forward. So the question is, how far will it move it? Well, now instead of looking in the vertical direction, right, this was our vertical direction, we're going to look in the horizontal direction. So we're going to switch gears here. We're going to say, okay, now we're in the horizontal direction. Same equation. Let's use the same equation. D equals VIT plus 1/2 AT squared. Except this is a one-dimensional equation. We've got to be better than that. We need to use it in 2 dimensions. So we have to pick one and apply it. We're going to apply it to the horizontal direction. So not just any arbitrary displacement, but a horizontal displacement. Not any initial velocity vector, but our initial horizontal velocity. Times a scalar, so it doesn't care about direction. Plus 1/2 our acceleration. We only want a horizontal acceleration. And again, times a scalar, so it doesn't care about direction. And so if we plug in the values that we had previously written down here on our chart, our horizontal displacement is what we're solving for, x. How far did the ball travel? Vx initial, well, we said, hey, that's 3.2 meters per second. Times our time interval t. And then look at this quadratic term right here, 1/2 ax, our horizontal acceleration, times time squared. We had mentioned that the horizontal acceleration of any projectile is 0, so that term drops away. And so we have 3.2 meters per second times our time interval. What is our time interval? It is the 0.4 seconds that we said that's the time the ball has to fall. So we get 3.2 meters per second times 0.4 seconds. And if I do 3.2 times 0.4, I get a horizontal displacement of approximately 1.28 meters. So there's a really nice projectile problem for an object rolling off of a surface. Let's quickly talk about a problem where a ball is launched. Are there any other questions right now at this point? Yeah. Oh, we do. What do we have?
Well, we were asked for a modern physics problem like E equals MC squared in unit
Perfect. Okay, so let's quickly talk about a launch problem, and then I'll do a modern physics problem. Imagine if I have a ball that is going to be kicked at some angle. So it's going to be kicked with some initial velocity, v initial, and we'll just say 5 meters per second. And I'm kicking it at an angle of, let's just say, 20 degrees. All right, and we know that ball is going to go up, and it's going to come back down. And so same concepts hold here. We are going to keep quantities separate, horizontal and vertical, all those good things. And so the first thing that we're going to say is our initial velocity vector is in 2 dimensions. It's got a horizontal component. I'll draw it in right here, Vx initial. And it's got a vertical component, Vy initial. So the first thing that we have to do is we have to solve for these components. And this is just trig. We've already seen how to do this. I have an adjacent side. I have an opposite side. So we'll do this really quick here. To solve for Vx initial, the adjacent side, adjacent and hypotenuse is cosine. So I'll take the cosine of 20 times my hypotenuse of 5, and I get an initial velocity of we'll say 4.7 meters per second. To get Vy initial, it is the opposite side of my triangle. So opposite and hypotenuse is sine. So if I take the sine of 20 and multiply it by my hypotenuse, I get a vertical velocity of 1.71 meters per second. Now that I have those values, let's look at how we might determine the amount of time that the ball is in the air. Well, we pick a direction. We'll pick the vertical direction, so the vertical direction. And we're going to use our kinematics equation, right? D equals VIT plus 1/2 AT squared. But now here's where it gets tricky. So I'm going to just quickly, let's convert that to the vertical direction. So I'm going to apply the vertical direction to all of my vectors so I don't accidentally mix in some horizontal quantities. And here's the trick. You got to know. What is the vertical displacement of this projectile in this scenario? If you think about it, displacement is just the distance from the starting position. You started at the ground, you went up, but you ended back at the ground. So in the vertical direction, what's the ball doing? It's going up, and it's coming back down. So the vertical displacement is 0. Vy initial, well, we solve for it in the diagram, is 1.71 meters per second times time plus 1/2 our vertical acceleration of any projectile is negative 9.81 meters per second squared times t squared. This is a quadratic equation, and so one of the things that I would recommend doing is just dividing everything by t and turning it into a linear equation, because 0 divided by t is still 0, right? That happens. And then you have to distribute this division. So the t's cancel here, and you get 1.71 is 1/2 of negative 9.81 is negative 4.9. And then t squared divided by t, you will lose this squared, and you get a t here. We'll subtract 1.71 over. And so to solve for our time interval now, we divide 1.71 divided by 4.9. I'm getting rid of the negative signs because they're going to cancel anyway. And the time the projectile is in the air is about 0.35 seconds. So kind of a similar analysis to what we saw before, but in this time we had to make a couple of different assumptions here. We had to assume that the displacement in the vertical direction was 0. To find how far the ball moves, the range of the object, it's the exact same thing. We now look in the horizontal direction. And we say, OK, we're going to take our equation, d equals VIT plus 1/2 AT squared, and let's apply it to the horizontal direction. X equals Vx initial t plus 1/2 AX t squared. We want the horizontal displacement. Vx initial, we broke down our initial velocity. Its horizontal component is 4.7 meters per second. Our time interval is 0.35 seconds. And 1/2 AXT squared, we said the horizontal acceleration of any projectile is 0. So that term drops away. And so we simply take our time interval and multiply by 4.7, and the horizontal displacement is 1.64 meters. There is one other quick type of question that you might get here, and that is, what is the maximum height that the ball rises to? So if we come back to our diagram here, the maximum height is going to occur right here. The maximum height occurs halfway through the range, all right, at its midpoint. So it's going to occur right here. And so what is y max? The way that I like to solve this is using a fact that we kind of have to know. In the vertical direction, Vy, what is the final vertical velocity at its maximum height? The ball is moving up, 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 and then it's about to come back down. So before it can come back down, the object has to come to rest and then change direction. So Vy final here is 0 if we call this our ending point. It is important to note that the velocity of the object is not 0. In fact, that ball still has an x component, Vx, of 4.7 meters per second at every single point, right? Because we know that the horizontal velocity is not changing. But we can use this fact to determine its maximum height. And we can do so, we'll say max height, using another kinematics equation. We'll use V final squared is equal to V initial squared plus 2AD. But we're going to apply this to the vertical direction. Vy final squared is equal to Vy initial squared plus 2Ay. And we're going to concern ourselves with the maximum height, so I'll call it Y max. At this maximum height, we claimed the vertical velocity is 0. So our final velocity is 0. Our initial velocity we solve for is 1.71 meters per second, plus 2 times our vertical acceleration of negative 9.81 meters per second squared, times our max height. So if I square, and I'm just going to do that work on the calculator here. If I square 1.71, I'm going to subtract it to the other side so it becomes negative. And then I'm going to divide by 2, and I'm going to divide by 9.81. I get a maximum height of about 0.15 meters here. All right, that's a really nice overview of projectile motion. The last thing that I'll just say here on this, and this is kind of like a quick question here, the optimal angle to get the farthest range is 45 degrees. 45 degrees is where you're going to maximize the amount of time in the air in relation to how fast the object is moving forward. So if you want it to go the farthest, it's 45 degrees. If you want it to go the highest in the air, its maximum height, the largest maximum height, that angle will be 90 degrees. So Carson, can you tell me what was that question that had come in again?
They asked to go over modern physics problems, including E equals mc squared and unit conversion.
Perfect. So let's go over a modern physics problem on the conversion of mass into energy. So I like to tell my students there's really two ways with which we can deal with these modern physics problems in converting matter into energy. There's E equals mc squared, or there is a direct unit conversion. All right, so there is a direct unit conversion. So we'll just say unit conversion. And here's the difference. When we use E equals mc squared, we have to be aware of what the units are required for this formula. C is the speed of light in a vacuum, 3 times 10 to the 8th meters per second. So you see, meters per second, that is a standard unit. So this formula requires a standard unit of mass, a kilogram, and a standard unit of energy, a joule. And in the macro world, if we're like tossing a ball or we're launching an object, energy in joule and mass in kilograms is pretty great. However, on the atomic scale, it might not be that convenient. So if we look at our reference tables, we actually have a conversion to convert mass on the atomic scale to mass, or energy on the atomic scale. And we can look right here, one universal mass unit, the U, is equivalent to 9.31 times 10 to the second mega eV. Now, this is the conversion of a new unit of mass, the atomic mass unit, U, into a new unit of energy, the electron volt. If you look at how it's written here on the reference table, I don't really like this. I don't like scientific notation with a metric prefix, so I will always write 9.31 times 10 to the second as 931 mega eV. And you may say, well, what does the metric prefix mega mean? If we look down here, mega is 10 to the 6th. So this is 931 times 10 to the 6th times 10 to the 6th. So we have a nice conversion. One atomic mass unit is 931 times 10 to the 6th. Now, let's look at an example where maybe we convert. Let's do a matter-antimatter collision. So let's assume we have. Let's do an electron and its antimatter particle. So I have an electron, and I have a positron. It's antimatter particle. So here is my electron, and I know I've got an electron, it's negative, okay? So a positron, what is a positron? Well, it's antimatter, and if you remember, we had mentioned this really quickly earlier. This is on our standard model page. For each particle, there's a corresponding antiparticle with a charge opposite of its associated particle. So a positron, instead of being negative, is going to be positive. And so we have oppositely charged particles, which means they are going to be attracted. And when they are attracted and when they meet, we're just going to say that they annihilate one another, and both of their masses are converted into energy. How much energy is converted? Well, let's look at this through E equals mc squared. So if I say energy is mass times the speed of light squared, energy is the mass that is being converted. So what is the mass that's being converted? Well, the mass of an electron, if you don't remember it off the top of your head, it's right here on the front of our reference tables. The rest mass of an electron is 9.11 times 10 to the negative 31st kilograms. 9.11 times 10 to the negative 31st kilograms. Well, we're not just converting the mass of the electron into energy, but the mass of the electron and the positron. These two things meet, and they both annihilate one another. So what is the mass of the positron? You can look all over your reference table, and you're not going to find it. So one of the things that you have to remember is that it tells us here, for each particle, there's a corresponding antiparticle with a charge opposite of its associated particle. The mass is the same. So the mass of our antiparticle is also 9.11 times 10 to the negative 31st kilograms. So we're going to combine those masses together. So I have 9.11 times 10 to the negative 31st kilograms plus 9.11 times 10 to the negative 31st kilograms times the speed of light in a vacuum, 3 times 10 to the 8th meters per second, and I square that. So if I combine my masses, let's see, 9.11 times 10 to the negative 31st plus 9.11 times 10 to the negative 31st, I get energy is equal to 1.822 times 10 to the negative 30th times the speed of light squared, 9 times 10 to the 16th. And so if I multiply by 9 times 10 to the 16th, I get an energy of, and now I'll make a note here. If you look at my calculator, the answer is 1.6398. For your physics regents, significant figures rounding to a certain number, you will not be penalized. So we can call this 1.64 times 10 to the negative 13th. And now we get to the point where we say, okay, what unit of energy is this? Is this, because if we look at like our energy level diagrams, we have energy here in electron volts. But if we look at our formulas, we're using standard units, kilograms, meters per second. This is an energy in joules. So what if we wanted that in electron volts? How would we now express this energy from joules? And if you see, it's a really small number, right? 10 to the negative 13th. How would we get it into electron volts? Well, it's just going to be a unit conversion. So if we look here, we define the electron volt, our energy at the atomic scale, as 1.6 times 10 to the negative 19th joules. And that number is oddly familiar to the elementary charge, because an electron volt, I believe, is defined as the amount of work you have to do to accelerate one electron through a potential difference of 1 volt. And so that's where we get this value from. So let's do this unit conversion right here. So I have an energy of 1.64 times 10 to the negative 13th joules. I open up a ratio. I want to get rid of joules, so I'll put it in the denominator. I want electron volts, so I'll put it in the numerator. 1 electron volt is 1.6 times 10 to the negative 19th joules. When I do this division, I know a lot of times my students will make this mistake. When you divide a number by scientific notation, always use parentheses. Otherwise, your order of operations are going to be messed up here. So when I do that division, I get my answer here. My energy is a pretty large number, right? It's 1024875 eV. But if we look, we often refer to this as mega electron volts, 10 to the 6th. So if I move my decimal point 1, 2, 3, 4, 5, 6, I get an energy of about 1.02, we'll say, mega electron volts. All right, so hopefully that was a nice problem that went over some of the modern physics and the relationship between mass and energy here, both from our standard units with joules and kilograms, and then our units that are more suitable for the atomic scale of atomic mass units and electron volts. Folks, how are we doing over here? Just hanging out. Well, if we look here, all right, well, I think we've done a great job. It's 8:19, so at this point, if you have any other questions, I'd urge you to maybe call in. We'll stay here just for another minute. Otherwise, just a reminder that your Regents is tomorrow at 8 a.m. You should show up with blue ink or black ink. Everything on the Regents needs to be done in pen, except for graphs, which can be done in pencil. You can bring your own calculator. Again, if you bring your own calculator, make sure that you have it set to degree mode, not radian mode. New reference tables will be provided to you, so if you had written notes all over your reference table, unfortunately you won't be able to use those. And you should be provided with rulers and protractors in case you get any nice vector diagrams or optics problems that you might have to solve. Just recall some of the tips that we started with here. We had mentioned that you should read each question carefully, underline key information, extract it from the problem, write down what you know, and then find a formula that has those values. And a lot of times, you know, the reference table is there for you to fall back on if you need it. And you can get by on a lot of questions with the reference table and your knowledge of algebra if you find yourself in a tough spot. I wish everyone out there that's still here at this point, I just want to say congrats. That's awesome that you're still watching at this point and you're still studying and working hard. I think it speaks very highly to who you all are as students. And I wish you all the best of luck on your physics Regents and whatever happens to you in the summer and beyond. So I think we'll end it here. Elise, Carson, why don't you guys come out, say goodbye to the people. Hey, there we are. All right. So thank you. Have a great night.